Welcome to this video from In 28 Minutes. Thanks for helping us provide awesome learning experiences to more than 300,000 learners across multiple platforms, Udemy, Safari, and Pact. Let's welcome our lead instructor, RANGA KARANAM. A lot of people think software design is complex, but we think software design is very simple when you understand the different principles which are involved. And that's what we would like to bring to you in this video. In this video, we'll be talking about the fundamentals of software design. Whether you are talking about designing your classes, whether you are talking about designing your layers, whether you are designing your components, anything that you design needs to adhere to these fundamentals. What are these fundamentals? These are coupling, cohesion, abstraction, and dry. So we'll start with discussing the basic fundamentals, coupling, cohesion, abstraction, and dry. And after that, we would think about the 4 principles of simple design and solid principles, which I think are awesome principles to understand to keep your software design simple. Dry is one of the 4 principles of simple design, and we'll also talk about 3 solid principles in depth: dependency inversion principle, single responsibility principle, and open closed principle. By the end of this specific video, you should have a good overview of how you should design your software. Let's get started with the first one in the next step. Welcome to this video where we'll be talking about cohesion. Cohesion is one of the fundamentals of how you design and architect your software. You'd hear a lot of people say you should have high cohesion. What does cohesion mean? What does high cohesion mean? Let's start with the basic definition of cohesion. Cohesion is all about grouping related things together. Let's take a real life example. There might be hundreds of things in your house, but whenever I would ask you something, you'd be able to easily fetch it within a few seconds or minutes. How? How is it possible? Let's say I'm asking for your tennis racket. You'd know where you'd put your sports utility stuff, right? So you'd directly go in there and you'd get it for me. You'd not go to a kitchen, you'd not go to your bedroom and search for it there. You might ask, how is this related to cohesion? The fact that you're putting all your sports stuff together, your kitchen stuff together, your sleeping stuff together, that's what cohesion is all about. Cohesion is all about taking that and putting it to software. Cohesion is about grouping related things together. The thing is, cohesion in software is applicable at multiple levels: methods, classes, packages, components, and applications, even microservices. You'd group related methods together and create them as a class. You'd take related classes together and create packages. You take related packages together and probably create components. Now, let's start with looking at a simple example for cohesion. Let's start at the ground level with some code. Let's take the example of this simple class. If you look at it, it's called download and store. What is it doing? Download from internet, parse data, store into database. So this method is aptly labeled to everything. It downloads from the internet, parses the data and stores into the database. So it does a lot of variety of things, right? It needs to talk to a web server and get the data. It needs some kind of a parsing logic, right? Maybe it gets XML, it gets JSON, whatever data format it gets, it needs to know how to parse it. It needs to know the structure of the response that's coming up and parse it. And after that, it needs to know how to talk to the database, JDBC or JPA or something like that, and store it into the database. This is a very good example of a class which has very less cohesion. Each of the methods in here are doing very different things. A better solution would be to have an implementation like this. You have a download and store class, but what does it do? It makes use of the internet downloader to download from the internet. It makes use of the data parser to parse the data. It makes use of a database storer class to store it into the database. Now you might be wondering why this is a better solution than this. This is a better solution because the chances of reusing something from here are more. Let's say this is not the only thing you are downloading and storing, and there are 10 other things. Then what would happen is all the database related activities would be either in this class or in that specific package. All the parsing related things will be together, and all the downloading related things can be together. There might be common elements which might be present along with them, which will help implementing stuff easier. When we develop applications, we develop them in terms of layers. We have a web layer. All the UI logic is in here. Think about cohesion. All the classes in web layer are related to the UI logic. Think about the business layer. They contain all the classes which have business logic, so it's highly cohesive. Think about your data layer. It knows how to talk to the database. You might have an external interface layer which might be understanding how to talk to external applications, maybe using a web service, maybe using MQ. But the important thing is each of these layers is highly cohesive. It does one thing. This one talks about UI, this one talks about business logic, this one talks about how to talk to the database. This is another good example of cohesion in play. Another good example of cohesion is common components that you develop across your applications, right? How you authorize and authenticate your users might be similar across all the microservices. So if you create a security component which only knows security, which only handles whether it's the right user, whether he has the right access and things like that, this component can be reused across multiple microservices. That's possible because this is cohesive. This is only handling the security aspects. I'm not trying to combine hundreds of different features into this component. The more features you add to it, if I make it security, logging and 10 of other features, then the reusability of that component goes down. Because security is one cohesive feature, including authentication and authorization, I can create it as a separate cohesive component. Similarly, I can create cohesive components for logging, maybe for auditing and things like that. One of the best examples of cohesion that I have found is implementation of the Spring framework. Spring framework is not implemented as one big component. It's divided into modules and it's developed as a number of smaller components. The core functionality, the core feature of Spring framework is dependency injection, and it's built in this container components, beans, core, context. The AOP is implemented as a separate module. Messaging is implemented as a separate component. Your Spring MVC framework is implemented as a separate component. Accessing data, JDBC is a separate component. ORM is a separate component. Transactions is a component on its own. And with the evolution of microservices, Spring Cloud is also a set of different components. It's not one big huge component. The reason is again cohesion. Each component has its own boundary and it does one thing and does it very well. The more cohesive it is, the more reusable it is. If I want to use Spring framework, I just need to use this basic stuff. If I want to also use JDBC, then I can add in JDBC component on top of it. By making sure that Spring framework is built as a group of modules, it's more reusable. Now, you might be wondering, how can I make software more cohesive? The only thing that you need to worry about when you want to make software cohesive is think about single responsibility principle. Think about your class, your package, your component, your module, and think what is its responsibility. If you are able to explain it in one sentence, then that's very, very good. If you are adding a lot of ends to it, this and that and that and that, then it means you might be violating this single responsibility principle, and maybe your component or your package or your class is not really cohesive. In this video, we talked about cohesion in extensive detail. We talked about the fact that cohesion is all about grouping related things together. Cohesion is applicable at multiple levels. You group related methods and create a class. You group related classes and create a package. You take related packages and maybe it becomes a component. We saw the fact that cohesive components are more reusable. Cohesive classes are very reusable as well. We talked about the fact that layering an application into business data and web layers ensures that each of these layers is highly cohesive. We saw how Spring Framework is highly cohesive by using a number of modules which have specific responsibilities. We discussed the fact that using single responsibility principle is the best way to build cohesive software. Until I see you another video, bye bye. In this video, we will be talking about coupling. We'll talk about what is coupling and look at a few examples of where coupling is and how you can reduce the amount of coupling between two classes, between two components, or any such kind of things. Let's start with a few examples to understand what coupling is all about. Let's say a friend of mine is building a Java component. He's delivering me a Java jar and I would want to make use of it. What is the constraint it puts on me? The constraint it puts on me is the fact that I have to use Java. Because the service he's offering is a jar, then I am coupled to using Java. How can I decouple? One of the things I can request my friend to do is not offer a jar, but I can ask him to say, create a web service around your jar. Once he creates a web service around the jar, this web service can be called from a Java application or a .NET application or a PHP application. What does it mean? It means we are decoupled from the underlying technology of the component. The component is in Java, but once we expose a web service, we are decoupled from the fact that the component was built using Java. We can use any kind of an application to call the web service. Let's look at another example. Let's say I want to use a specific module from the Spring framework. As we know, Spring is highly modularized and there are a wide variety of modules which are present in Spring framework. Let's say I would want to talk to the database and I would want to use a Spring JDBC. What do you think will happen if to make use of Spring JDBC, Spring says you have to use Spring JDBC and you have to use Spring Beans and Spring Context? What would happen? I'll not use it because I don't want to be dependent on so many things. I don't want to configure so many things to get just the JDBC working. The Spring framework designers got it right in the sense that you don't really need Beans or Context to use JDBC. You can directly use JDBC without needing the other ones. JDBC is not really coupled to other modules of Spring. Now, let's get a lot deeper and look at a code example. Let's look at a simple shopping cart example. What we have in here is a shopping cart entry, which is like a specific item. So I would want this much quantity of an item of this specific price. And we have a shopping cart which has a list of such items, right? So when I am shopping, I would probably buy 10 different kinds of items. So you maintain a list in here and you have an order which calculates the sales tax around it. So it uses the sales tax and calculates the total price. Pause the video in here and spend some time and look at this specific implementation for the order. What you'd see in here is that this method knows the internal details of shopping cart and the shopping cart entry classes. It is accessing directly the items and then it's accessing directly the price and the quantity. Think about a situation where you change the name of this variable from price to something else. What would happen? This order class would also change. If you change this, the order class would also change. If you change the fact that items is an array and make it, let's say, some other kind of a list, this class again would need to change. This order class is tightly coupled to the shopping cart and the shopping cart entry classes. Now, how can we decouple it? The way we can decouple it is by providing better information, better interfaces from the shopping cart entry and the cart contents classes. So the shopping cart entry, instead of saying this is the price, this is the quantity. What we are doing in here is we are providing a method, get total price. So we'll not expose the price and the quantity, but only expose the total price, price into quantity. Now what does the cart contents do? It exposes another method called get total price. It loops around the items and calculates the total price and returns it back. What does the order do? Order calls cart dot get total price and adds the sales tax to it. So now you can see that if this variable name changes, the only thing which would change is the shopping cart entry class. If the items name changes or the structure changes, what is the only thing that would change? It's the cart contents class. And this order class is now decoupled from the implementation of the cart contents and the shopping cart entry classes. Isn't that awesome? The way you can think about coupling is, if I make a change to the inner details of something, should I change something else somewhere as well? You don't want that kind of stuff between two different components. If I want to reuse something, what are the dependencies? It should be as minimum as possible. As with cohesion, coupling occurs at multiple levels. What we are looking at is coupling at class level. We looked at the example of a web service where we reduced coupling at a API level. Coupling can also happen at component levels. For example, if security component is dependent on the logging component, then if I would want to use the security component, then I have to also use the logging component. That's coupling at a component level. How do we reduce coupling? We already looked one example of it, right? So we created a web service to reduce the coupling with a specific technology. We created proper methods and we exposed as minimum data as possible so that we decoupled individual classes. Let's look at another example. Binary search IMPL. The thing in here is this binary search IMPL class is directly dependent on the bubble sort algorithm. This is again coupling. What if I have to change it to quick sort algorithm? I would need to change the code of the binary search IMPL. Now, how can I solve it? I can solve it by creating an interface called sort algorithm and have the sort algorithm as one of the dependencies in the binary search IMPL. If you're using Spring Framework, then you can put at autowired on the sort algorithm, and Spring Framework would be finding the right sort algorithm and auto-wiring it into the binary search IMPL. What we are doing in here is we are reducing the coupling between binary search IMPL and a specific implementation of the sort algorithm. Let's consider another example. Let's say I have a web layer, a business layer, and a data layer. And for a specific requirement in the application, let's say from the web layer controller, I would need to call multiple business methods. Let's say I have to do 5 different business method calls to satisfy some requirement on the web layer. How can I avoid that? One of the ways you can avoid that kind of coupling is by using the facade pattern. You can create a facade at the business layer which takes care of invoking all these 5 methods, and the web layer can just call the facade component. In this video, we looked at coupling at different levels. We said the key question related to coupling is, if I change a specific thing, would something else change as well? If I have to use something, then should I use something else too? That is what is called coupling. We looked at coupling in multiple levels, starting from code, components, and APIs and frameworks. We saw multiple examples of how you can reduce coupling between code, and we saw how you can reduce coupling with a specific technology. When we reduce coupling, our code, our components become more reusable and also more testable. It becomes much easier to test those components. Until I see you in another video, bye-bye. In this video, we will be talking about abstraction. Abstraction is one of the fundamental concepts of software engineering, how you build your applications. Abstraction is all about hiding complexity. Let's say I want to drive a bike. All that I need to do is put the key in, press the start button, and use the accelerator, or sometimes the brake. Am I really worried about how the engine is working, how the brake is working. Nope. All that is really abstract to me. I don't really worry about it. Let's take the example of trying to print a document. You just say file, print, and after a few minutes you would have the document printed in the printer. Are you really worried about the fact that the computers only understand 0 and 1? Are you worried about how data is being transferred from your computer to the printer? Nope. That's another example of abstraction. Whenever we build applications, we build them in layers. Why? Because the web layer does not need to know anything about the data layer. It is abstracted away from the data layer. All that it needs to worry about is, okay, I can delegate this to a business layer and it would take care of it. It does not need to really worry about what happens in the business layer. So layering of your applications is, in a way, abstracting away complexity. Think about your programming languages. At the basic level, we would have done some assembly language programming. But do we really write assembly language programs these days? Nope. All that we would be doing is writing Java or Python, high level languages. So you'd be writing programs in human readable languages. You are no longer writing programs in zeros and ones. That's another example of abstraction. Think about the SQL queries that you write to get data from the database. You just specify what data you want. You don't really worry about how that data is retrieved from the database. You just write the query and you expect the database to go and get the right data for you. That's another good example of abstraction. Using the methods which are built into your programming language is a good example of abstraction as well. Here I'm calling a method hello world dot ends with world and it returns back true. I don't really need to worry about how ends with is implemented. All that I need to understand is if I call ends with any word which ends with the right thing, it would return me true. Same is the case of hello.is lower. I don't really need to worry about what is the implementation. It's abstracted away from me. All that I need to care about is the fact that there's a function. When I call, I know what the result is. Abstraction is one of the pillars around which entire thing around software engineering is built around. Whenever we talk about programming, methods, classes, design, all that we are trying to do is abstract away complexity. Let's look at an example of microservices architecture. In microservices architecture, typically we have common components for security, logging, archetype. Why do we want common components? Because we want these common components to take care of specific functionality. Let's say you want to handle authorization and authentication. That is handled by your security component. So your security logic is abstracted away into this component. All these microservices will use this component and will need to know how to make use of it. They don't really need to worry about what is the inner level details of these components. That's another good example of abstraction. In this step, we talked about abstraction. We said abstraction is all about hiding complexity, and we looked at a number of examples around abstraction. Until another video, bye-bye. In 28 Karanam. In this video, we would be talking about something called DRY. Do not repeat yourself. What is it all about? Whenever we talk about programming, one of the things which we hate is duplicate logic. If you want everything in your code, whether it's a method, whether it's a class, whether it's a package or a component, to do one thing and do it very well. You don't want repetition of code. You don't want duplication of code in multiple places. That's what DRY tells you. Don't repeat yourself multiple times, especially in your code. One good example of DRY is writing a method and writing an unnecessary comment. Writing I is equal to 1 and say in the comment I is assigned a value of 1. Why do you want to repeat yourself? Later, when you make I is equal to 3, the comment gets outdated very fast, right? So do not repeat yourself. Do not repeat yourself also applies at a higher level. Always try and think in terms of components. If you see some logic being common to multiple microservices, try and create a component for it. Try and create a security component. Try and create a logging component. Don't repeat the same logic in multiple microservices. Try and create common APIs or common components. Try and adhere to the single responsibility principle. So, try is kind of a philosophy that we should always adhere to as a programmer, as a designer, as an architect. If you see things repeating again and again, if you see patterns emerging again and again in your code or between your applications, between your APIs, try and put them in a common place. Try and reuse them. That's what Dry is all about. In 28 minutes is providing awesome learning experiences to 3. Welcome back. In the previous video, we talked about the importance of keeping design simple. In this video, we'll be talking about 4 principles of simple design and how they would help us to keep our design simple. One of the important things with Agile is the recognition of the fact that requirements change. So your aim with most of the Agile projects is to meet your today's requirements with clean code, with easily understandable code, and go for complex design only when simple design does not solve the problem. So it's always important to start simple, and when your requirements get complex, then you can start using more complex patterns. So the most important part is things change. So it's very important to be prepared for the change. And how do you get prepared for the change? Is by having very good automation tests, unit tests, integration tests, and API tests. It's very important that all these are automated. You have simple design. And what are the 4 principles of simple design? The 4 principles of simple design are: runs all tests, contains no duplication, expresses intent of programmers, and minimize number of classes and methods. Why is it important that code runs all the tests? Because you would want your code to work, right? So it's very important that your code is working at all the times. An important corollary to this is the fact that you should have a lot of automation tests. You should have unit tests, you should have integration tests, you should have API tests, which are all automated. You should be able to run them as part of your build. And all these tests should be running in continuous integration. That means as soon as you commit code in, all these tests should be run and you should have immediate feedback. So runs all tests ensures that your software is being tested all the time, so it's stable. One of the most important design principles is to have as minimum duplication as possible. Earlier we talked about common components. Why do you want to create common components? Because you don't want the same logic being present in multiple applications. Creating common components will help to centralize the logic and other applications can reuse it. Similar to that, different components, different packages, different classes in your code should not have duplication. When you have duplication, you have the same code residing in 2 or 3 places. And that means whenever there's a change, you need to change all these 3 places. And that's a big sign of bad design. Good design contains very less duplication. The third important point is expressing the intent of programmers. Your code should be easy to read. Your design should be simple. Anybody who looks at your code should be able to understand what it's trying to do. I would recommend you to pause the video in here and try and understand what this piece of code is doing. Try and pause the video here for 1 minute and move on. Now, let's look at another example of the same code. Pause the video in here and look at what it's trying to do for 30 seconds. This code is actually a result of applying the 4 principles of simple design to this code. The first objective was to make the code more understandable. How do you make the code more understandable? Is by giving good variable names, is by creating methods with very good names. Those are the 2 fundamental things for expressing clarity: variable names and method names. Once you have good variable names and method names, you can easily create classes with good names and it flows up from there. Express intent of programmers is also called clarity of code. Your code should be very clear that anybody who looks at it will be able to understand it very fast. The last principle of simple design is all about having as less code as possible. You need to have minimum number of classes and methods, and these methods and classes should be very small. So small methods, small classes, and a minimum number of them is a very important part of having simple design. So you should achieve your business functionality with as minimum code as possible. In this video, we looked at the 4 principles of simple design. These 4 principles help you to keep your design very, very simple. Your first aim when you are writing some code, you are making a design, is to adhere to these 4 principles of simple design. And when you adhere to these 4 principles of simple design, you can start thinking about what more things that you would want to add. I'll see you in the next video. Until then, bye-bye. Welcome back. In this video, we'll be talking about solid principles. As it says in here, don't dare to violate them. What are the 5 solid principles? The 5 solid principles are single responsibility principle, open closed principle, Liskov substitution principle, interface segregation principle, and the dependency inversion principle. Let's start with the first one, the single responsibility principle. Single responsibility principle is all about having only one reason to change. Whether you're talking about a class, whether you're talking about a package, a component, or an application, they should all have one responsibility. You should be able to define what an application is doing in a single line. And when you are able to achieve your single responsibility principle, you would see that the amount of possibility of reuse would increase. Look at this specific class. It's responsible for downloading something from the internet, it's responsible for parsing something, it's responsible for saving that data to the database. Is that meeting the single responsibility principle? Will I be able to reuse this kind of code in anywhere else? The answer is no. Let's look at another example. This is actually doing a calculation of a pay, it's creating a report, and it's saving the employee details to the database. These are classes with multiple responsibilities. So, single responsibility principle is all about having classes which do one thing. The second most important principle is the open closed principle. It says software entities should be open for extension but closed for modification. What does that mean? Look at this implementation of calculating area for a shape. You're passing in an array of shapes and we are checking if a shape is rectangle, then do this, else do this. What if I have to add a few more shapes? All the logic would be centralized in this specific piece of code. So whenever I add a new object, then I should start modifying all the code which is present in the area method. Now, what would be a better solution? The better solution would be allowing each of the shapes to define their own area methods. So here we are creating an abstract class called shape. This could also be an interface. And we are creating a area method inside the rectangle class, implementing the abstract method in here. The area method would only be responsible for looping around them and calling the area method on the specific shape. So this area method is now having only the logic to loop around the shapes and add the areas in. This is a very good example of open close principle. Now, if you want to add a new shape, you don't really need to change the area method. So this area method is closed for modification. You don't need to change this. But we are open for extension because whenever you would want to create a new shape, all that you need to do is to create the shape and define the area method inside it. So we are open for extension, open for new shapes, but we are closed for modification. We don't really need to change the area method. The third principle is the Liskov substitution principle. One of the things people tend to do in object-oriented programming is try and use inheritance even when it's not really the right thing to do, just for the sake of reusing the code. Liskov substitution principle says subtypes must be substitutable for their base types. Let's consider an example. Let's say there's a rectangle class and we have a set width and the set height method which is implemented, and we have a get height and the get width method as well. And now there is a new requirement to implement a square class. And what I do is, instead of trying to implement a square class on its own, I would try and extend the rectangle class. So let's say I would say square extends rectangle, and I create a set width method where I would set both height and width to W,
and I would do the set height method where it sets both height and width to h. Is that a good implementation? Liskov substitution principle says it's a bad implementation. Consider a piece of code like this, right? So if somebody wants to test a rectangle, let's say this is the method which is written. r.setWidth 5, set height 5, and he's checking if the area is 5 into 4. Will the square class pass this test? The answer is no, because your set height is actually setting both height and width to the same value as h. So what would happen is set height 4 will set both height and width to 4. So the area would be 4 into 4 and it will not be 5 into 4. You should always be careful when you use inheritance. You should use inheritance only when your superclass is replaceable by a subclass in all the instances. Don't use inheritance just to save a few lines of code. The fourth principle we will be talking about is called the interface segregation principle. When two systems or two classes are talking to each other, then they should have the smallest possible interface that is defined. Why is it important? Let's take an example. Let's say I have an animal interface which is having an abstract feed method. We are creating two classes, dog and tiger. Implement the feed method. Let's say now I would need to add a feature to groom. What would happen if I add the groom method to the animal interface? What would happen is the dog and the tiger need to implement the groom method. Groom is something which should only be applicable to domestic animals. So I can groom a dog, but for a tiger, I'm providing a dummy implementation just to keep the compiler happy. Is that good implementation? The answer is no. The ideal way to handle that would have been to create another interface called pet. Instead of adding features to the existing interface, it's better to create a new interface called pet, extending the existing interface and adding the groom method in. The dog can extend the pet interface because groom is applicable to it, but tiger would continue to extend the animal interface. That's what interface segregation principle is all about. Keep your interfaces as small as possible. The moment you have fat interfaces with a lot of methods, then every time you change the interface, then it means that all the implementing classes also should change. The fifth principle that we will be talking about is the dependency inversion principle. It says depend upon interfaces or abstractions rather than concrete classes. What does that mean? Let's look at an example. Look at this implementation of the copy method. What it's doing is based on the output device which is passed in, which could be printer or a disk, whatever is read from the keyboard, it would be written down to the output device. So you can see the logic for it in here, right? So you read it from the keyboard and you are checking if the output device is printer, then write to printer, else write to disk. Now what is the problem with this? The problem is as your number of output devices increases, this copy method needs to keep changing. A better implementation would be to create a simple interface like reader and have an interface writer. And the copy method can write from any reader to any writer. So the copy method does not change when you have a new writer or a new reader. This is a good example of a dependency inversion principle. In this video, we looked at solid principles. The idea was just to quickly introduce you to all the principles with a few code examples. We looked at single responsibility principle, we looked at open close principle, we looked at Liskov substitution principle, and we looked at interface segregation principle as well as the dependency inversion principle. I'll see you in the next step. Until then, bye-bye.
RANGA KARANAM. In this video, we will be talking about dependency inversion principle. Dependency inversion principle says depend upon abstractions and not upon concrete classes. What does that really mean? Let's take an example. Let's look at this specific example where we are trying to copy to an output device. We want to read stuff from the keyboard and copy it to an output device. And look at this specific implementation of it. So we are taking it using read keyboard. So what it's doing is it's directly accessing the keyboard as the input, and depending on the output device, we are writing to a printer or writing to a disk. This copy method has a number of dependencies. for example, the input device, the output device and stuff. But instead of declaring them as dependencies, what it's doing is it's directly accessing them, directly creating instances of them and taking the responsibility of talking to them directly. A better way of designing that would have been to create an interface called reader, an interface called writer, and the copy method is only responsible for reading the interface and writing whatever it gets from the interface to the writer. Now, what is happening in here is we are leaving it to the user of this specific method. So whoever is using this method, they can create instances of the reader and the writer and pass it in. The copy method would read from whatever reader is provided and write it to whatever writer is provided. So instead of instantiating the reader or the writer by itself, copy method is saying, okay, these are dependencies for me. I'm not going to worry about them. You send me anything and I would make sure that whatever is got from the reader is sent out to the writer. Dependency inversion principle is also one of the core things that Spring Framework enables. Look at the example down here. So this binary search IMPL is directly going ahead and creating an implementation of the bubble sort algorithm. The bubble sort algorithm is a dependency of the binary search IMPL. What is happening here is the binary search MPL is directly creating the dependency. What is the disadvantage of doing that? Now let's say I want to switch from bubble sort to quick sort. I would need to change the code for this. Instead of that, the binary search IMPL can declare this as an dependency and let a framework or the external class provide that dependency. Let's look at how you can have implemented it now. A better way would have been to create an interface called sort algorithm and have the binary search IMPL make use of the sort algorithm. In this specific example, what we are doing is we are creating a constructor. So we are saying when you are creating the binary search IMPL, also pass in an implementation of the sort algorithm. So whoever is using this class can either send in a quick sort or a binary sort. Thereby, we are decoupled from which sort algorithm to use. So this binary search IMPL does not worry about which sort algorithm. Whatever sort algorithm you are providing it, it would use it. The dependency inversion principle is all about not creating the dependency yourself. Make sure that you define your dependency and let the classes which use you or the components which make use of you provide an instance of the correct dependency. By using the dependency inversion principle, you'd make your code more testable. Instead of passing in the real version of the dependency, your test code can provide a mock or a stub and you can easily test your code or component. In this video, we looked at the basics of the dependency inversion principle. Until another video, bye bye. In this video, we would be talking about another important principle with respect to object-oriented programming, open-closed principle. Your classes should be open to extension but closed to modification. What does this really mean? Let's look at a simple example. Let's look at this specific implementation of an area method. This area method takes a set of shapes as a parameter. And if you look at the logic of it, what is it doing? It's looping around all the shapes and it looks if the shape is a rectangle. If rectangle is there, then it calculates the area for that specific rectangle. If it's a circle, then it calculates the area of the circle. Let's say there are 10 other shapes which I would need to write the logic for. What would happen? This method would become big and big and big. This example is a clear violation of the open-closed principle. Now, let's look at how it can be implemented. One of the first things we can do is we can have an area method in the shape class. If you're a Java programmer, then the area method has a capital A. That's not really right. It should have been small a, but that's not really important for now. So we have an interface or an abstract class. One of these can be a proper solution with an area method. And we have each of the shapes, rectangle, they implement the area method. So you have a circle also implementing the area method. So we implemented a common interface or an abstract class shape, and we have all the shapes, rectangle and circle, implementing that. This area method now just is responsible for looping around the shapes, calling the area method, and summing up the area. Now think about this from the perspective of an open close principle. What happens when you have a new shape? What do we need to do? We need to create a new shape, let's say a polygon, and implement the area method for it. Do we need to really change the area method which does the sum? Nope. This area method is closed for modification because it would be able to handle all kinds of shapes. All that the shape needs to define is its own individual area method. So you can easily extend it by creating a new class which implements the area, which extends the shape class, and this area method would be able to calculate the area of all the shapes that are passed to it. So this is a very good example of being open for extension. So we can extend it by creating new shapes which implement the area method, which extends the shape class and implement the area method. But we have made the area method which calculates the sum of all the areas of all the shapes closed for modification. Open closed principle is always about creating software entities which are open for extension but closed for modification. Until I see you in another video, bye bye. In 28 minutes. Welcome back. In this video, we would be talking about the single responsibility principle. We would be talking about what it is and how you can apply it in your software career. As the principle says, it's all about single responsibility, one responsibility. Thing is, the single responsibility principle is applicable at multiple levels. Whether we are talking about a method, whether we are talking about a class, whether we are talking about a package, a component, or an application, this single responsibility principle is applicable to all of them. Any method that you would write should have one responsibility. Either it should be a high level method or a low level method. Only when a method has one responsibility, you'd be able to give it a very good name. Same is the case with a class. You should be able to tell what a class is doing by just looking at its name. When we talk at a low level, at the level of a class, I can define single responsibility principle as a class should have just one and only one reason to change. Let's look at an example. Look at this specific class, public class task, download file, parse the file, persist the data. If you look at this specific class, is it adhering to the single responsibility principle? Nope, because it's doing a lot of different things. It's downloading the file, parsing the file, and persisting the data. It's talking to the internet and downloading something, it's parsing something, it has logic to save some data to the database. So that's a lot of different responsibilities that this specific class has, and that's not adhering to single responsibility principle. A better way to approach that problem would have been to have different classes with specific responsibility. Have a class for downloading from the internet, have a class for parsing the data, have a class for storing it into the database. And then you can have another class at a high level which is responsible for invoking the methods in each of these classes. This would ensure that each of these is reusable. So this class can be reused somewhere else if I have to download something else, or this parsing logic can be reused and things like that. This is another example of a bad class, because this specific class is now worried about how to calculate the pay, how to calculate reports, how to do saving to the database. As we discussed earlier, single responsibility principle is also applicable to layers and components. Let's start with looking at components. In enterprises, you have common components. For example, a security related component which handles the authentication and authorization. This would help us to abstract ourselves from the low level security details. So all the microservices can use this component to find out if a user has a specific role, has a specific access, is it the right user, and things like that. As far as possible, these components should have a single responsibility. So the security component should only do security stuff. It's less reusable if you do a component which handles security and also logging or does multiple responsibilities. So even at the levels of components, the more you'd be able to have well-defined responsibility, a well-defined single responsibility for a component, the more reusable it is. Implementing location transparency. All the microservices would register here, and whenever they want to find about another microservice, they would ask the naming server. API gateways responsibilities are also unique. The responsibility of a centralized logging is just to act as a store for all the logging so that we can easily debug problems. You don't want a single system doing multiple things. So single responsibility applies both to your components and also your infrastructure tools. Single responsibility also applies to how you layer your applications. All the things which handle user requests, which are directly communicating with the user, are inside your web layer. All your business logic is in your business layer. All the data related stuff, all the things which involves storing, retrieving data are in the data layer. If you had messaging, if you are talking to other systems, then probably there's an enterprise integration layer which takes care of that responsibility. So even your layers are having single responsibility. In this video, we talked about the single responsibility principle. We talked about the fact that at a basic level, the single responsibility principle is all about making sure that a class has only one reason to change. A class has just one responsibility. Similar to that, you would want your packages, your methods, you would want your components and your applications to have one well-defined responsibility. When you have one well-defined responsibility, it would ensure that you have high cohesion, low coupling, and you are reusable. Until another video, bye bye.
Now that you understood the principles of software design, I'm sure you'd be excited to learn a lot more about design and architecture. I would recommend you to visit the GitHub page, which is in the link of this video, to find out about a lot of other videos we are creating about design and architecture. In 28 Minutes is providing awesome learning experiences to 300,000 learners across platforms like Udemy, Safari Online, and Pact. We have clocked million hours of learning in the last few months. The question is, what do you want to learn next? We are building solutions to help programmers at all levels. You can learn programming with our awesome courses on Java, Python, and JavaScript. You can learn full stack development with REST APIs and microservices with a wide range of frameworks like Spring Boot, Node.js, React, Angular, and Spring Cloud. We have 200 plus videos to help you start your journey from a programmer to a software architect. We have videos to help you learn frameworks, industry trends, including things like microservices, learn the best practices in architecture, design, and code quality. Thanks for watching. Keep learning in 28 minutes.